Okay, in this video, I'm going to go through the solutions to problem set 8. Okay, and problem set 8 is from chapter 9. Okay, so we're going to start off with the first problem is in section 9.1. It's going to be exercise 9.1, and this is based on the change problem. Okay, so in the US, so it asks you to write an algorithm that takes some number n, okay, which is the number of cents, okay, again in a US version. And then this array D is going to be all the coins that you can use, okay? So in the US, for example, we would have, starting with the biggest in common use, a 25, a 10, a 5, and a 1, okay? Other countries could have different things, okay? So the idea is to give change back using a greedy algorithm, okay? So, and if you don't have a 1, there's a possibility that you won't actually get the exact same change. So we have to allow for that, okay? So again, we have an algorithm. I'm going to call it change that takes this n and this d with 1 to the number of n's that you have. Okay. Number of coins, number of denominations that you have. So the input then is going to be a non-negative integer amount n and a decreasing. Okay, so this is decreasing. Has to be. Okay. The output then, that's our input. Our output is going to be, and these are all in comments. Output is going to be this array C from 1 to m that basically shows how many of each coins that you have. Okay, so again, in the US, we have these coins. So C will have how many quarters, how many dimes, how many nickels, how many pennies, based on that, okay? So that's the idea there, okay? So for this, we're gonna have a for loop here. We're gonna go from I starting at 1 to m, okay? So we're gonna do each of our coins. We're gonna check all the coins to see if they're part of our change. We're gonna let C sub I, so C for whichever coin that we're on, okay? Be able to, or going to get here, the floor to get rid of any fractions of n divided by d sub I, okay? So what that's going to do, for example, if we had our n being equal to, I don't know, 35, okay? This step, so for the C sub 0, which is the 25, is going to be equal to that 35 divided by 25, the floor of that, which is 1, okay, because there's 1/4 in that, okay? We then have to change what the n is. So n is going to get n times the mod of d sub I, okay? That kind of undoes the division you did before, okay? So in our case, from this, n would now be equal to 10, okay? And you're going to stay in that loop until you do all the different coins. So in our case, the quarter, the dime, the nickel, and the penny, okay? So again, for our example, this C is going to look like we're going to have 1/4, we're going to have 1 dime, 0 nickels, and 0 pennies, okay? So when we come out of the loop, we have to check to see if our n is equal to 0, okay? If it is, we're going to return that array C with all the coins, okay? The else here, we're going to return the string no solution, okay? Again, that's only possible if you don't have, if you have a coin of a denomination 1, you're never going to have it, okay? So that's the first problem. That's problem 1 from 9.1. We also have problem 9a, okay? Let's look at 9a. I'll get in the book here, okay? So 9a is, am I in the right section? Sounds like I'm not. Okay, we got that. Okay, I'm in the right section. Okay, it's going to be a Prim's algorithm. Okay, so we're going to have prims on the following. We've got an A, we've got a B, we've got a C, we've got a D, and there's an E in the middle. Okay, and there are lines everywhere. The following weights: a 5 there, a 7 there, a 6 over there, and a 4 down there. And then a 2, a 4, a 3, and a 5 in the middle. Okay. So for this solution, remember we have to start at some position. Okay, so we're always starting at one of our vertices. Okay, we're going to create a little table here with 2 columns. We're going to have the tree, it's 2 E's, tree vertices. And we're going to have the priority queue of the remaining vertices. Okay, so we start off at A. Randomly, we can start off wherever we want. But let's assume we start at A. Okay, A, there's nothing. That's where we start at. Then we look at what's left. Okay, we can get to B. A to B has a cost. You were at A and it's a 5. Okay, C has an A7. That's the one down there. Okay, we can't get to D, so it's A infinity, and E has an A2. Okay, because that is the quickest. Okay, so again, we have A already. Okay, so the one to pick is the E2. We pick that, and that gets added to our tree we're creating. Okay, so we've added and then the E, which is an A2. And we do the same thing again. Okay, we now look at B, and our quickest way to get to B is through E3. Okay, so remember with this, unlike with Dijkstra, we don't have to start at A every time. Okay, for C, we can now look at an E4. Okay, and the D we can now get to is an E5. Okay, so again, the one to pick there is the B. Okay, so we have our B, E3 over there. The B gets added, and that line gets added as well. Okay, so with the B gone, we now just have the C. And C, our quickest way to get there, okay, is from E. We also from D is the same, but there's no reason to switch unless there's a reason to switch. So it's an E4, and the D is still an E5. Okay, so we pick the C. Pick the C from E, from there. Okay, so now we have wrong color. Now we have our C of E4 there, which just leaves our D. Okay, but now D, the quickest way to D is now from C. So we add a D of C4 instead of the D or the E5 that we had before. Okay, so that's our minimum spanning tree. Okay, it's the AE edge, it's the EB edge, it's the EC edge, and it's the CD edge, which is the minimum spanning tree. Okay, so that's what that one looks like. Move on to section 9.2, where we have 1A, which again is going to be another minimum spanning tree, but this one with the crystal. So we have an A, we have a B, we have a C, we have a D, we have an E. Okay, the weights as follows: 1, 5, 6, 3, 4, 2, 6. Okay, and remember with the crystal, how it's different from prims is that we're going to add the edges that are sorted, okay, by the ones with the smallest value, but we can't create a cycle, okay? So if we have our sorted list of edges here, okay, so we have the tree edge that we're going to add, and then we have our sorted list of the edges, okay? If you look here, you have BC is 1 is the smallest, DE at 2 is next, followed by BD at 3, CD at 4, AB at 5, AD at 6, and CE is also 6, okay? So we're adding this BC first, okay? When we add the BC, we're going to add this connection here, okay? And then both B and C have been dealt with, okay? We're next going to add the DE, okay? So the D is going to be in our tree and the E is in our tree. Those get connected up, okay? But it's edges we mostly care about here, okay? Then we try to add the BD next, okay? We can do that. BD works, okay? CD, we try to add that, and we cannot. That makes a cycle from B to C to D and back, okay? So we can't add that one, okay? We can go to the AB, okay? And that's okay. And once we've added that, we now have our minimum spanning tree. We don't need the others, okay? So the AB, BC, BD, and DE make the minimum spanning tree of this one. Okay. On to section 9.3 on Dijkstra's algorithm. Okay. So in it, we're going to take a similar looking graph, but not exactly the same. Okay, so this one is directed. Okay, it doesn't have to be, but it turns out that it is. We've got an A, we've got a B, we've got a C, we've got a D, we've got an E, and we have a 3 there, we have a 4 there, we have a 5 to there, we have a 2 back that way, we have a 7 that way, we have a 6 that way, and we have a 4 that way. Okay. So with the Dijkstra, we're going to again create a table. And the table we're going to create here is as follows. Okay, we're going to have the tree, can't spell tree today, tree vertices, and we're going to have the remaining vertices. Okay, from this graph. And everything starts from A. It's A to everything else. Okay, so we start with our A, which again has no predecessor and it's where it's at. Okay, the remaining from A, B, we can't get there from A, right? Because of the way the arrows go. Okay, so there's no predecessor and it's infinity. Okay, can't get to C either. So it's a dash infinity. Okay, the D we can get to with the 7. It's the only one we can get to. So E is also an infinity. Okay, so the vertices we're going to add then is going to be the D. It's all we can add. Okay, so we've added that now. Okay, so we add the D over here, which was that A7. Okay, now we can go from A or D, but we have to count from A. So B is still here, okay, but the last one it was at was D, and it's a 7 plus a 2, okay, or a 9, okay. We can get to C, the 7 plus 5, okay, which is a 12, so it's a D12, okay. E, we still can't get to, Okay, so E, we're still at that. Okay, so the shortest one there is the B. We add the B at D9. Okay, so B gets added in, that gets added in. Okay, so what, now that we've added B, all we have left is a C, wrong color, a C at D12. Okay, and we still can't get to E. E is still at infinity. Okay, so the C has to be added, no way around it. Okay, the C being the D12. Okay, and we can now get to E, our E being a C. It's the 12 that we had to get to C plus 6 more, okay, or 18. So E, C, 18 is the last thing that we have. And that puts it in there, okay? There are then 2 questions about that, true false questions on 9. And is this a minimum spanning tree if you make this tree based on Dijkstra? And the answer is yes. We're covering all of, we're getting to all of the vertices, and we're not doing any cycles. So it's a minimum spanning, it's a spanning tree. Is it a minimum spanning tree? Okay. And it turns out that it's not. It doesn't have to be. I mean, it could be. It doesn't have to be. Okay. In particular, that plays on the fact that we're always coming from A. Okay. So if we have the following counterexample here. So if we have an A, and we have a C, and we have a B. Okay. And these simple forced examples are typically the way we're going to prove these things. Okay. So if we're going to use Dijkstra on this, the shortest path, we're going to add the A to B. Okay. And because of the longer distance around, okay, the A to B to C versus A to C, we're going to add the A to C. Okay. Because it has to come from A. Okay. This is not the minimum spanning tree. The minimum spanning tree would be here. Okay. So the second part is false, and that's a good counterexample why. Okay. The last thing was the Huffman encoding. And the first problem is to create the Huffman code for the following data. This is very much like the example we had in the book. So we've got the character and the probabilities here. We've got an A, we've got a B, we've got a C, we've got a D, and a dash with the probabilities of 0.4. Let's see the points: 0.1, 0.2, 0.15, and 0.15. Okay. So you start by making these little nodes for these. Okay, and you're going to put them in order. Okay, so at the very left hand, okay, we're going to have the B. Okay, it's the lowest. Okay, so there's a 0.1 here, which is a B. The next one is going to be the D at 0.15. You could have put the dash, doesn't matter. We just kept them in the order they were in here. Okay, we have the dash. Sorry, that's a 0.15 is the dash. Okay, we then have the 0.2, which is a C. We have the 0.4, which is the A. Okay. And then you're going to be combining these from the left and then reorganizing. Okay. So these two come together to form a new one. Okay. It's going to be 0.1 plus 0.15 is 0.25. It's going to come down to the B and to the D. Okay. But that now has to be ordered in here. It now goes all the way over there. Okay. So to rewrite that, okay, we're going to start with the 0.15 and the dash, the 0.2 and the C, and now the 0.25 with the B and the D, okay? And still on the right, the 0.4 with the A, okay? You now combine these two together, okay, to make a new one. Let's go ahead and sort these in place. So when this becomes the 0.15 and the 0.2 become a 0.35. So this 0.25, right, as I'm saying it, 0.25 is going to go in the end with the B and the D, okay? The 0.35 is now in the middle with the dash and with the C, okay? And you still have over here the 0.4 with the A, okay? We now combine these two together, okay? When you combine those together, you get a 0.6. So the 0.4 and the A comes first. Over here, you have the 0.6, okay, which goes into the 0.25 and the 0.35, okay, which goes again into the B and the D and the dash and the C, okay. You finally combine those two together, okay, you can draw that here, into a 1.0 that now goes there and there, okay. So that's your whole tree. You can then assign zeros for the left and 1 for the right of each of these, okay, which gives us the following table, okay, that A is represented by a 0, B is represented by a 1, 0, 0, okay. So again, in blue for the B, it's 1, 0, 0 to get there, okay. The C is going to be a 1, 1, 1, okay, 1, 1, 1. The D, get rid of those again, went too far, went too quick. 1, 1, 1. The D then becomes, we do the same way, it's going to be a 1, 0, 1. The dash is a 1, 1, 0. Okay. And then from there, it's relatively straightforward to take your message. Okay, so for example, it's almost time for class, so I got to be quick. So the ABA, first part of that would be a 0 for the A, 1, 0, 0 for the B, 0 for the A. Okay. And then on the translation, it starts off 1, 0, 0, 0, 1, 0, 1. Okay. The 1, 0, 0 is a B. The 0 is an A. The 1, 0, 1 is a D, and so forth from there. Okay. And then for the last problem, that's the one that you may or may not be able to figure out. Okay. I just wanted to get your brains working on this. Okay. So let's talk about how we're going to solve this. So with this, we're going to create a diagram. Okay. The probabilities here of the ace is 1 out of 45. Okay. A probability that's a deuce is a 2 out of 45. Okay. Probability that's a 3 is 3 out of 45. Probability that's a 4 is 4 out of 45, and so forth, all the way up to a 9 being 9 out of 45. Okay. You can do this just like a regular Huffman code. Okay. And you're going to combine these two together. Okay. So this becomes a 3 out of 45. Okay. That this way goes into the A, ace, and this way goes into the 2. Okay. You will then keep combining those down, okay, until you find a way that you can ask questions such as, is the selected card a 4, 5, or 9? Okay, and then from that, you could then pick and navigate your way through. Okay, so hopefully that makes sense. Okay, I'm hoping that is a reasonable explanation. If it's not, then make sure that you let me know.